So now we're going to revisit the last example that we did again. So we're going to sketch the graph real quick, reasonably accurately once again. 1, 2, 3, 4 in the x direction, 1, 2 in the y direction. We know the square root goes up to there. We know our line starts at 2 on the x-axis and then meets our square root. And then they're all held together with the chunk of the x-axis necessary to enclose this area. However, we had to do two separate area integrals. And the question here becomes, is there anything stopping us from integrating with respect to y? So what are we going to do here is we're going to imagine that we're going to integrate this thing with respect to y. So, okay, we're going to take slices and add them up. And so it looks like, well, from 0 to 2 would give us this. And if we integrated from 0 to 2, you could imagine kind of finding all those Riemann sum, all those rectangular little thin slices of area from 0 to 2. Traveling from 0 to 2, well, what are our top and bottoms going to be? Well, what used to be our top was our line, y equals x minus 2, can easily be solved for x to be x equals y plus 2, and that is our top expression. Okay, so what is our bottom expression going to be? Our bottom expression is going to be, well, it used to be y equals square root of x. So squaring that on both sides would give you x equals y squared. And x equals y squared, if you drew the rest of that, I know this isn't part of the square root, but if you did continue it, you would get the sideways parabola, not a function in terms of x, but a function in terms of y. All right, so that is now our bottom. Okay, so let's try this and see how it goes. The area between, we should get the same answer, is going to be, well, we're going to integrate from 0 to 2, and our top function is now, well, actually, before we fill in our functions, when you decide to integrate along the y-axis, you're integrating with respect to the variable being y. I like to actually start by putting our differential in there, and then that kind of helps me figure out the logic over here where I take the original functions and say, hey, I need to solve them for x so that they will be in terms of y, so that I can integrate them in terms of y. So our top function is y plus 2, and our bottom function is y squared. Let's do that. That's nothing fancy. We can do that. What has the derivative of y? 1/2 y squared does. Has the derivative of 2? Well, 2y does. And what has the derivative of y squared? 1/3 y to the third power. All that jazz evaluated from 0 to 2. This gives us, for y is equal to 2, 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 to the third power minus the bottom guy, y equals 0. 0 plus 0 minus 0. Be careful when you're evaluating something for 0. It's not always that you're going to get 0 if it's like something to the 0th power or something. But in this case, it's just a polynomial plugging in a bunch of zeros for all the variables. It's going to just be 0. So that's done. All right, so this becomes 1/2 times 4. 4 times 1/2 is just 2 plus 4 minus 8/3. 2 plus 4 is 6. So you get 6 over 1 times 3 over 3 minus 8/3. 6 times 3 is what, 18 I want to see? 18/3. And this smells like we're going to get the correct answer. Minus 8/3, 10/3. Same answer as before. So sometimes if it's really challenging to figure out those two areas, if it feels like the problem has to be broken up into two separate area integrals, sometimes you can integrate with respect to the other variable easier, and you'll always get the same result, which is nice.